my particular topic was to look at the selective activation of chemical bonds by coherent terahertz radiation. Since obtaining the award, I've interviewed and appointed two postdoctoral research fellows, one Alex McIntosh, an organic chemist, and the other Bin Yang, who is the antenna engineer. They've got on quite well, and we've managed to move on from initial reading and preparation for how we would do the experiments, planning for the experiments, so that what we will show from Alex and Bin's work is how they've received the quasi-optical circuit, and it's been applied now in initial measurements, both to check performance against established data and also to make excursions into new areas. The work over the past 6 months is being summarized in an article, a tutorial paper to the Chemical Society Review, and it will set out how metrology is being developed for applying the vector network analyzer, which is the centerpiece of this work in terms of the way it's being newly radically applied to activating chemical systems. And it's being developed in tandem with the another coherent piece of experimental kit called the time domain spectrometer, which works at higher frequencies overlapping with the vector network analyzer. So from here we'll cut to the terahertz lab, where you can see the instrumentation and have the initial experimental procedures looked at, and we'll wrap up with a look forward to the next 6 months in terms of how we hope to demonstrate activated control over chemical processes by the vector network analyzer in a very tuned and deliberate manner.
The new network analyzer from HP, and it can basically working from megahertz to 43 gigahertz. But for this project, we got some extension head to millimeter wave band. So the current frequency can extend from 75 gigahertz to 325 gigahertz. It can give us a very rich frequency source. And the advantage for network analyzer is its high dynamic range and megahertz high resolution compared with traditional terahertz system, whatever TDS or FTIR. And this new generation of network analyzer can give us huge advantages to observe the molecule spectrum. The basic signal from network analyzer is, for example, from 12 gigahertz to 18 gigahertz. And then if we put this extra extension, it's called the millimeter wave head extension, the frequency will be harmonic multiply 18 times to cover currently this band 220 to 325 gigahertz. The energy from this head will be a little bit drop, but basically it's still in milliwatt range. So there's still very good advantages for this millimeter wave head. And currently we got these a pair of two corrugated horns. This horn this hole 1, this hole 2, and these two horns has another advantage. It can reduce a lot of standing waves in the optical systems. In whatever in TDS or in FTIR and other people, for example, we go back to low frequency microwave. In measurement system, people always get this standing wave to damage their result. So, but for our case, this a pair of corrugating hole can significantly kill plenty of standing waves, makes the spectrum very clean, and we can avoid a lot of noise. And also the last one for this Z-bench optical bench. And for example, I give a quickly demonstration. The basic polarized beam will go through from this hole, come here, and the beam will be converged to small size to this fast mirroring hole. This fast mirror hole will quickly reduce the big beam to very, very small, the radiation just 1 millimeter, to shining to the sample in this position. Currently, we put this Okin-Dankin sample here. So that means the whole area, the optical intensity is significantly enhanced by 60 times at this point. So we give the sample a lot of energy to radiate for this millimeter waves response. Thus, we can find a lot of interesting information at this point. And then the signal will continue going, focused by another focus mirror, and then to this focus mirror back to another corrugating hole. We get a clean signal. And the signal will be read by this network analyzer.
The first thing we did was just review the literature, essentially. And part of that has been to write a review paper, which in the process of submitting at the moment. And then from that we've kind of gleaned what systems are accessible to the VNA, which has been spoken about, sort of up to 325 gigahertz. So the primary systems we've seen are these alkanes, higher chain alkanes, octadecane, ecosane. So we've been able to prepare samples like this, as they have done in the literature, rapid cooling, fast cooling. It's analogous to infrared spectroscopy. We'd mix samples with an inert matrix, in this case polyethylene, and then it's mixed in various ratios. Then it's compressed using a dye press up to sort of 8 tons pressure, and then they sort of pop out like so. And then obviously it's a process of characterising those really well, just weighing what mass has gone in, the mass of the pellet afterwards, thickness. So we've got those really well characterised, so when we actually come to do the experiments, we know what we're kind of dealing with. A lot of this, say, is just getting to the bottom of how well we're producing those, because analogous to kind of when you manufacture tablets, because they're very similar to how you make tablets in the pharmaceutical industry. So it's about mixing things and getting the correct mix and making sure reproducibility. So produce 5 pellets that are all producing the same results. So octadecane is prepared slightly differently. That's kind of from a melt, that's cooled down really slowly or really rapidly using a Dewar flask. And that can lead to different crystal phases being formed.
Now that we've begun to identify ground rules for using the VNA system for chemical work, and being concerned with the issue of metrology in terms of the way we're using the system, what we're wanting to do is, over the next 6 months, is for us to access higher frequency heads, as they're called, that we can extend the range of the vector network analyzer from its current upper limit of 320 gigahertz to a full terahertz. And it means that we can have access to a larger range of solid-state systems, particularly in terms of what we can seek to demonstrate control and manipulation by coherent radiation. So we've already demonstrated our ability to observe processes with the octadecane and the transformation between crystal phases as it goes through an excursion from high to low temperature. What we're wanting to explore in the next 6 months in parallel with the chemistry is to exploit the vector network analyzer to simultaneously perform as a standoff thermometer. We will seek to effectively have it operate as a pyrometer in the way we exploit the shape of the absorption spectrum to estimate a temperature for the reaction process, so that as well as exciting a particular chemical process and afterwards observing the result of the activation, we also seek to acquire basic information about temperature, for example. So this is a very new and radical advancement in terms of the way the vector network analyzer seeks to be used. So that will largely dominate the work for the next 6 months, as well as perfecting methods and experimental procedures that we've established in these first 6 months. And as we discover what modifications are required for the current quasi-optical system. But the main message is that the two PDRAs are working well together, and useful material is already coming out that we're able to publish. So for the first 6 months, we've made fairly quick progress in terms of acquiring the hardware early, because preparations were made in anticipation of being awarded the grant. So lead time was dramatically reduced, which means that we've had more time for preliminary procedures and development work, so that it's the next 6 months that promise to be the most productive in terms of really getting into the task of coherent activated control of chemical reactions.